I'd like to talk about pitch training research using auditory feedback. The title is Auditory-centered vocal feedback system using sonimization for training absolute pitch without GUI. Let's play a simple quiz. Can you guess the note name of the sound? If you could find the pitch, you have the potential of the absolute pitch. Absolute pitch is the ability to name or produce a note name of a given musical tone without an external reference tone. Absolute pitch is a not essential skill. However, having absolute pitch can sometimes be beneficial, especially for professional musicians. One interesting thing is that most individuals having absolute pitch state that they hear music as words rather than envisioning it as notes. This study proposes an auditory-centered training system using sonimization to artificially acquire and train absolute pitch by providing vocal feedback of musical notes through a musician's voice.
So sharp, do sharp C, re sharp, so sharp, fa.
Currently, most absolute pitch training systems provide musical notes names and pitches via graphical display as visual feedback, which is the feedback of information via user's vision. However, as I mentioned before, most individuals having absolute pitch state that they hear music as words rather than envisioning. Therefore, our proposed method adopted a musical note singing method called sonimization. This is a method of singing while calling out each sound by its note name, like do, re, mi. And sonimization provides singers with vocal feedback of notes in form of words, facilitating pitch training. And here, vocal feedback refers to the feedback of information by a user's hearing by speech with corresponding pitch. Furthermore, our proposed system does not require graphical user interface, in contrast to traditional training systems such as tuners or the visualized guide melody of karaoke. We inspired some HCI studies using vocal feedback. One study has demonstrated the potential of non-visual feedback in the design of accessible memory games. The results were especially better when haptic cues were presented in combination with speech-based cues. And the other proposed a method to assist the writing rehabilitation. The system was designed for human-in-the-loop operation, and it could analyze handwriting in real time while providing vocal feedback to guide the patient during exercise. These studies indicate that auditory feedback is useful for providing simple information like up, down, left, right. The research question for this study is, can absolute pitch be trained by a vocal feedback system? Extant pitch training methods provide visual feedback containing the note information. However, individuals with absolute pitch describe their experience as audible instead of visual. Furthermore, previous studies indicate that auditory feedback is useful for providing simple information. Our contributions are as follows. First, we constructed a pitch training system that allows users to recognize note names orally via sonimization. Second, we compared this vocal feedback system with visual feedback systems as a counterpart, and identified which type is more effective in pitch training. This figure shows the design of our proposed system. It consists of 5 modules. In short, user controls slidable to change the question pitch, and the system feedback the sound and visual information depending on the training mode. I will explain the detail from the next slides. This is the user interface of the training system. It consists of 3 modes: vocal feedback, visual feedback, and pitch test. In the vocal feedback training mode, the user imagines the pitch of the given note name, for example, re, which is also called D in English note name. Then, user operates the slide bar by mouse to change the oscillator sound. At the same time, the user listens to the vocal feedback of note name with correct pitch. At that time, the user tries to memorize the association between the note name and the pitch. Then the user listens to the exact correct pitch. Finally, move to the next question. In the visual feedback training mode, the user gets the visual feedback of staff notation and the note name instead of vocal feedback. So it's like to be this. While operating the slide bar, the user sees the staff notation and the note name and listens to the brief sound in the current pitch. In the pitch test mode, they need to guess the exact correct pitch of a given note name by controlling the slide bar. They only hear the oscillator sound when controlling slide bar. And press Enter button if the user confirms current slide bar position as non-answer. After pressing the Enter button, the note name of the current slide bar position is displayed as the input note name. So the user checks if the answer is correct or not. And finally, move to the next question. This is the simplified hardware setup. The user controls the application with mouse and listens the auditory feedback by headphone. So, there is a hypothesis. We anticipated that vocal feedback of the note presented by the proposed system would be more effective in improving the absolute pitch than the visual feedback of the existing system. So we conducted an experiment to measure the effectiveness of both systems to improve the absolute pitch. We recruited 10 people with no reported physical or mental disability. An experiment consisted of a preliminary test and a main test. Main test consisted of the 3 tasks: vocal feedback training, visual feedback training, and absolute pitch test. We prepared 2 patterns to reduce the possible bias caused by the training order. 5 participants trained on the proposed system first, and the other 5 trained on the existing system first. In this experiment, the participants were trained in absolute pitch using both systems, and they took test C before and after the training A and B to quantify the improvements of the absolute pitch. Since we accepted participants regardless of their musical experiments, we did a preliminary test for grouping purpose. Using an existing pitch training application, the participants attempted to absolute pitch quiz 10 times and recorded their scores. 4 people who recorded perfect scores were defined as potential absolute pitch, and the other 6 were defined as non-potential absolute pitch. All potential absolute pitches had experience playing the piano or electric piano. In contrast, all non-potential absolute pitches had neither experience playing the instrument nor lessons of any musical instruments except for the class in the school. This is the result of the experiment of potential absolute pitch. Here, error means the difference between the correct pitch and the user's answer. For example, if the correct pitch is C, but the user answered it as C sharp, the error will be 1.0, which means a semitone interval. The average error is the average difference between the correct pitch and the input pitch from the 10 questions in the test task C. The improvement value refers to the difference between the average error before and after the training. And generally, neither the proposed nor the existing system showed significant improvement. The average improvement value was slightly negative in both proposed system and the counterpart. This is the result of non-potential absolute pitch. Generally, the proposed system showed some improvements, whereas the existing system didn't. In the proposed system, the average improvement value was 0.65. In particular, participant 4 had an improvement value of 1.40, implying that absolute pitch accuracy improved by more than a semitone. In contrast, in the existing system, the average improvement value was minus 0.49. In non-potential absolute pitch, all participants' improvement value were positive in vocal feedback training. In contrast, the improvement value of the visual feedback system was almost negative, except for one person. As a result of Wilcoxon signed ranked test for comparing the average error before and after the training in the proposed and existing system, it shows significance only when people with non-potential absolute pitch trained with the proposed system. This is the distribution of the pitch improvement values in the proposed system between non-potential and potential absolute pitch. From this figure, it is clear that non-potential absolute pitch had a higher improvement value than did the potential absolute pitch. This is because the potential absolute pitch scores before training was already high, so the score after the training was unlikely to change. This is the result of the self-evaluation of the participant's sense of the pitch before and after the experiment. Although some participants responded that they felt their sense of pitch improved slightly, there was a little influence in their self-evaluation of the absolute pitch. Additionally, we asked whether the existing system or a proposed system could be used for long-time training, for example, 1 hour per day for a month. And as a result, 80% said that they would like to use the proposed system for long-time training. When they asked about improvements, there was a desire for multiple choice of feedback voice and for shortening the long word sharp. One provisional solution will be to use German note names system. In German note names, we can call the sharp note as sharp note name shortly. For example, do sharp called cis in German note name. Although we adopted GUI-based slide bar as the system input for pitch control in the experiment, vocal feedback system can be non-GUI application by using user's voice or instrument as the system input. Also, in this study, the experiment was designed for training absolute pitch. However, initially, it could also train relative pitch. For example, if someone plays the note E and you have in your head already a note C, you can compare the two and notice that interval of the major third is formed. So thank you for listening.